Right, so let's get started. So, hello everyone, so this is SeungryongKim. So today we all finished the least scale problem or least scale solution part. This is lecture 11. So lecture 11. I think today's lecture is very short compared to the other our previous lecture. So let's finish today's topic. So right, let's briefly review what we've done. Right, so here is the definition of the least scale solution. 여기서부터 합시다. Here's the least solution. 여기서부터 합시다. So, give the matrix A, whose size was n by n, and T is in Rm space. Least scale solution of Ax equals B. Least scale solution of the Ax equals B, where Ax B doesn't have any solution because this is inconsistent system. Anyway, least scale solution of the Ax equals B is going to be the x hat that should such that length of the p minus ax hat is smaller or equals to p minus length of the p minus ax, where x is any vector is in Rn space, which means like x hat is going to be the make ax the closest point in the column space matrix A to the B. So which is called, I mean the x hat. In this case, x hat is called the least square solution. So something like this. So given a column space, 그렇죠? Given a matrix A, column space W, vector B hat, vector B can be projected to the AX hat, which is also a projection of the B onto the column space. Then in this case, where we can find the least square solution X hat for the AX hat is equal to P hat. So in other words, we have to find out X hat, 그렇죠? Where P hat is also projection of the B onto the column space matrix A. And finally, so based on some kind of property like the P minus AX hat should be also known to this vector P hat, which is equal to AX hat. So like this, so we can finally say rewrite the new equation like A transpose A times A transpose A times X hat is equal to A transpose B, like this, which is equal to A transpose first of all, this equation is called AT A transpose times A X hat is equal to ATB, which is called the normal equation. In other words, the solution for this normal equation is called the least square solution. This is the least square solution. So, right. So in other words, the set of the least square solution of the Ax equals B coincide with the non-empty set of the solution of the normal equation AT-AX is equal to ATB. The solution. This solution is going to be the least square solution for the original linear system like Ax equals B. That's what I want to do today. Right, here's the example. Let's do together. So first of all, you have a X equals B, where A is like this, 2 by 3 matrix, and P is equal to 3 by 1 matrix. 3 by 1 matrix. Let's find the least square solution for this inconsistent system. So first of all, this is inconsistent system. So this is inconsistent system. You can easily check this system has solution or not, which is our previous topic before the midterm exam. So today let's use the numerical equation like AT-AX is equal to ATB. So 다시 써볼까요? Numerical is going to be AT-AX is equal to ATB, where AT is like this, AT like this, A is like this, so it's going to be by row column row, like first row and first column, it's going to be 17, blah blah blah. ATB, A transpose and P, it's going to be the 1911. You can easily compute this one. So, in other words, AT-AX is equal to ATB. It's going to be our numerical equation. So, because we know ATA, this is the like this, because ATB is going to look like this. So, first of all, we can just find out the solution for this one, which is a least square solution. And we can just check this is consistent system. Consistent system. There are many kinds of way, but this is the, how to say, because this is the square matrix, ATA is a square matrix, you can just find the inverse of the square matrix. 그렇죠? So we already talked about how to find the inverse of matrix, 그렇죠? But because this is 2x2 cases, we can easily find out inverse of matrix by using the rule, like AB minus BC times A, DA more negative BC, like this. So it's going to be 1 over 84 times 5, negative 1, 17. You can easily, you can just find the inverse of matrix part. Then anyway, because it has this matrix invertible, I mean the ATA is invertible in this case, solution for this numerical like x hat is going to be inverse of ATA times AT times B. Inverse of ATA is like this from this one, 그렇죠? And ATB from here is going to be like this. Finally, this one is going to be 1/2, 1,2. So this is the least square solution, right? Very easy. So first of all, this solution does not satisfy this system, original system, but this is going to be the optimal approximate system solution. That's the least square solution. Right, so this is a least square solution. So from now we'll talk about one more theorem, like right. So where matrix A whose size was n by n. Following statement logically equivalent. I mean the whole true or whole false. First of all, equation x equals b has a unique least square solution for each b in Rm space. I mean the uniqueness of the least square solution. Second one, columns of matrix A are linearly independent. Columns of matrix A are linearly independent. Third one, matrix ATA is invertible. Then least square solution is unique. Okay, so before proving this one, this is just one example. Previous examples is just one example of this one. Because matrix A are linearly independent and ATA was invertible, as you can see here. So solution was unique as a 1,2. In other words, columns of matrix A are not linearly independent, or matrix ATA is not invertible. X equals B does not have any unique least square solution. In other words, AT is not invertible, columns of matrix A are not linearly independent, X equals B does not have any unique least square solution. So they are logically equivalent. Let's prove this one today. First of all, columns of matrix A are linearly independent, which means like A, x is equal to 0. I mean the homogeneous system always only have a trivial solution. 그렇죠? Right. Then based on this, A transpose A, when we multiply A transpose on left hand side and right hand side, ATA x is equal to 0 because AT times 0 is equal to 0. So it means that here ATA x is equal to 0. Because this is the square matrix. It just follow the IMT, invertible matrix theorem. So it means that because it satisfies this equation, ATA is invertible. Right? So if ATA is invertible based on this observation, solution X is unique as X hat is equal to ATA inverse times ATB. Unique. In other words, you have to find a solution for this one. If this numerication does not, if numerication inconsistent, then you have to find a solution for this. It's not inconsistent. If numerication does not have any unique solution, then you have to find out number of solution for the least square solution. That's the theorem for the theorem. Right, so yeah, let's find out one more example. So let's find the solution, least square solution for the x b, where a is like this, 4 by 2 matrix, b is the 4 by 1 matrix. First of all, two column vector, let's say a1 and a2. Because the two column vectors are orthogonal, so you can just check a1 inner product a2 is equal to 0. So orthogonal operation of the b onto column space matrix A given by b hat. Where is that? Yeah, b and column space matrix. First of all, in this case, column vector matrix, vector x a1 and a2, orthogonal basis for the column space. So you can just find out p hat following this rule. So by comparing this one and this one, it's going to be the 8 over 4 a1 plus 35 over 19 times a2. So from here, from this relationship, first of all, b hat is going to be like this, like this. And now that b hat is known, we can just solve ax hat is equal to b hat as a here, 그렇죠? Because this is like a times x, 그렇죠? By rewriting matrix A and x. Then we already know we can just say, right, this one and this one, it's going to be the solution. So for I have 8 over 4, 45 over 90, so which is going to be 2, 1 over 2, which is going to be the least square solution. So that's the alternative way to calculate the least square solution. But you can just use this rule. If there is inverse, there exists the inverse of the invertible ATA. So, but if not, you can just solve the least square solution by doing like this. So, that's it. And one more thing is that in some cases, numerication for the least square problem can be ill-conditioned. That is, small errors in the calculation of the entries of the ATA can sometimes cause the relative large errors in solution x hat, which means like, right, so our numerication was like ATA, which was the square matrix, and x times x is equal to ATB. So in either case, I mean in calculation, there's no error. But as we discussed in our previous lectures, like the pivotal tuning, pivotal tuning. This square matrix, I mean because we in computer programming, you just use like the floating point. I mean the fixed size of the bit to represent your floating point number. So it means like, so when your some matrix value contains some error, when you just compute the inverse of this matrix, like this, some error can be maximized or boosted in inverse of this matrix. So it's not usually appropriate, right? So alternatively, I mean the more practically, the least square solution can often be computed more reliably through the QR factorization of matrix A. We just discussed the QR factorization in previous lecture note. So from now on, to solve the least square solution, we can just use the QR factorization, because this is a more reliably, this is a way to more reliably estimate the least square solution comparing to this original numerical solution. That's the theorem 15. So given n by n matrix A with linear independent column, so it means that it always has the unique least square solution. Why? Based on this one, 그죠? Linear independent columns induce the unique least square solution for the ax equals b. So anyway, in this case, like a can be factorized to the qr because the a has a linearly independent columns. So then let's say that b is in Rn space. Then a equals b has unique least square solution given by x hat is equal to or inverse q transpose b, rather than just like a inverse of a transpose a times a transpose b. We can more reliably or simply represent x hat unique least square solution as R inverse q transpose b. This is another way. 자, proving this one is very simple. Proving this one is very simple. For example, x hat is equal to R inverse q transpose b. Then ax can be represented by qrx hat because the a is equal to qr, and then x hat can be replaced to here. Then it's going to be r inverse q transpose b because this one is equal to identity matrix and this one is equal to identity matrix. It's going to be like p. So in other words, cos of q form an orthogonal basis for the cone space matrix A. So that's the definition of the q matrix in QRF decomposition. QTB is going to orthogonal operation of p hat or p onto the cone space matrix A. That's the definition. So it means that ax hat is equal to b hat, which show that this is not a zero vector identity matrix. So this one is cell. So let's say this is a b hat. So anyway, ax hat 그쵸, because the q times q transpose is not an identity matrix, right? Sorry. So let's say this is a b hat. Anyway, ax hat is equal to b hat, which show that x hat is the unique least square solution of the ax equals b. So anyway, uniqueness of the x hat follow the theorem of like this one, because a constant matrix A are linear independent. That's it. So this is proving. Anyway, so from now on, if your matrix A can be factorized to the QR, you can more effectively, reliably comparing your least square solution. So why? So more specifically, comparing to this one, A transpose A. Maybe it can contain some error, but in this case, it also has an inverse matrix R, but as we discussed in QRF factorization, R has some very, very good property. First of all, this is a square matrix and diagonal term always has a positive value. That's why the inverse of this matrix R is much reliable comparing to the stable, or reliable comparing to the inverse of A. That's it. That's all. That's also the reason. Anyway, x hat is going to be our inverse q transpose b. That's it. Least square solution. Right, so that's it. So far in this lecture note, we discussed how to find out solution, even though your system does not have any solution. Even though your system is in continuous system, so that's called the least square solution. So we talked about how to define the least square solution and how to derive, how to compute the least square solution and how to determine uniqueness of the least square solution. So that's the whole of thing I want to let you know today. So thank you very much, and please recap. This is just a lecture video. So please, if you have any question, please let me know. And let's see lecture 12 next week. Right. So thank you very much, and see you next week.